Hi there, welcome to this video where we are going to dive more in depth on what functions are. Please like this video if you find it helpful, subscribe for more math content, drop a comment or question below to engage, and please check out the practice set on this lesson. Quick disclaimer, I do have my phone on vibrate, but now not only am I waiting to hear about my apartment, which still has holes in the ceilings, but also I have a car in the shop. So I'm waiting to hear about both of those things. Hopefully, I won't get interrupted in the middle of recording, but this is life. So apologies in advance. Hopefully it won't be a disruption. Okay, wanted to start out with a summary of what we already know. And I am going to link right up here, a link to the previous lesson. So if you are hopping into this lesson and realize that you do not know what we are doing, I want you to go and check out that link right there. Click on that and then come back and join us after you have gotten caught up, okay? All right, so a summary of what we already know about functions. We have defined a function as a relation or a mapping, and that goes back 2 lessons actually to when we were talking about sets and the idea of mapping from one set onto another set, in which each x value maps to only one y value. X's are where our mapping originates, it's where it starts from, and then the y values is what we call where the mapping ends. And that relation or function is a specific kind of relation where this is true, where each x value only goes to one y value. The domain is what we call the set of x values. Okay, so it's got its own name. The domain is just all of the numbers that could be in that first set. We might list all the numbers in that first set, or there might be too many for us to list. In fact, very often it will be an infinite number of numbers, so we do not actually list all of them, but we can talk about them like the set of odd numbers or the set of real numbers or the set of prime numbers, okay? And those are inputs. That again is where our mapping starts. And the range is the name for all of the y values that are the outputs. That's where the mapping ends. And so you have this other set of numbers that could be all the things that you map to, and then we call that the range. So we have the domain and the range. Now, let's explore this further as it connects to equations, okay? Because as I mentioned, most of the sets that we work with are infinitely large. And so it's not practical for us to create these little bubbles. I mean, they're cute and they're kind of pretty. They make my slides look pretty, but they're not very practical. We would not want to indefinitely be doing these little bubbles. So we're going to use the pattern for this, 2x minus 4. So that's the pattern. Remember, most of the time we are interested in a pattern. If there's no pattern, we can't really do much with it. And so our y values are going to be equal to 2 times the x value minus 4. So I'm just going to pick like an x value. I'm going to pick, I don't know, 3. Okay, and I'm going to use this pattern right here. So 2 times 3 minus 4, 2 times 3 is 6, and 6 minus 4 is 2. So that means I have a 3 in the domain, and that means there is a 2 in my range, and the 3 will map to a 2. Let's do 2 times, we'll do 5. Okay, and 2 times 5 is 4, and 10 minus 4 is 6. So we have a 10 in our domain, and that maps over here to a 6. Let's pick a negative number. Let's do negative 1. So let's see. 2 times negative 1 is negative 2, minus 4 is negative 6. So negative, try again, negative 1 maps over to negative 6, etc. And so when you start really talking about domain and range, we might even say, well, like, is there anything I couldn't pick for my domain there? Like, could I pick like 1.5? Okay, so let's try like a decimal. We don't usually go there, but 2 times 1.5 is 3, and 3 minus 4 is negative 1. So we could like sneak that in, like 1.5 and that would map over here to a -1. Is it possible for us to get a decimal out? Sure, if I picked like 1.25, then 2 times 1.25 is what, 2.5, 2.5 minus 4. So yes, I could get decimals out, okay, as my y value. And what I want you to really notice there is that we're using this pattern, this 2x minus 4, and we're generating like this set of domain and range, like this set of mapping pairs. And sometimes what you will see instead of like the y is you'll actually see the expression written there, like 2x minus 4. Okay, and so you've got x, and then you have this 2x minus 4 instead of the y, and that just shows you, okay, this is the pattern that we're using to get there. The value for y depends on, and I had meant, and never went back and did it, I had meant to put that in italics, but we'll highlight it instead, okay? So the value for y depends on the value we pick for x. And then what you will hear in the future, probably not in this lesson so much, but is independent and dependent variable. The x value is independent. I'm sitting here just willy-nilly. I'm going to pick something. I'm going to pick 3 and 5 and -1 and 1.5. And it's independent. I could just go pick anything I want. But once I pick that, the y value I get is dependent on the value that I picked for x. And so we have this idea of the independent variable, which is typically the x, and the dependent variable, which depends on whatever we picked for x. This is essentially what it means to be a function, that you don't have these independent variables floating around, okay? So we say that y is a function of x, okay? And that is how we express this. We say that the y value is a function of the x value. That's how we express this dependence. That's how we say it in words, okay? So we've got maybe our everyday vocabulary, y depends on x. And then we have this more mathy sounding vocabulary where we say y is a function of x. And we abbreviate that with this notation right here. And somehow that turned back to yellow on me, okay? And we read that f of x, it's an abbreviation for function of x is what it is. So y is a function of x. You might see this, okay? Y equals f of x, or y is a function of x. And that f of x is this shorthand way of saying function of x, and which is a way of expressing this dependence. The y value depends on the x value. This is my dependent variable. This is my independent variable. So y depends on x, y is a function of x, and then this is what it looks like. Now, we're going to break down this notation a bit more because there is a very common but imprecise way of conveying these ideas. It is not correct to say that f of x and y are the same thing. And I want to be careful about how I say that because I am very quickly going to seem like I'm contradicting myself, but so I want to make this clear. The reason why f of x and y are not the same thing is because not all relations are functions, okay? Not every equation that you can come up with that has an x and a y in it fit that very specific definition of for every x, there is only one y that goes with it. Now, it is true that you can replace any f of x with a y. So I tell my students that all the time. If we're working with, something will go past the level of this video. So they're working with that. They got f of x, that function notation, and they're like, I don't like it. You can replace that with a y. Okay, it would be some extraordinarily rare situation that is not coming to my mind at the moment where you couldn't do that. And I usually tell them that, listen, if you're going to get the problem wrong because you don't like the notation, go ahead and change it up. But it is not true that you can replace any y with an f of x. So it's like that substitution only goes in one direction. If you have an f of x, then you can go back and replace it with a y, but you can't go the other way around and just take any old y and replace it with an f of x, because they're not exactly the same thing. The function is maybe a subset, okay? So if you've got like, these are all the things that you could use for y's, your f of x's are like inside that. It's a special kind of relation. So is it true that if you have a function, that f of x, that you could replace it with a y? Sure, because all of your functions like are kind of contained in there, but it's not true that every single y would also fall into that like little f of x bubble there. So that is something that I hear from students a lot, and I think they've often heard it in classrooms from teachers, and it's just getting a little bit lazy because a lot of times they are the same thing and you can just kind of get away with it, but they're not. So just be aware of when you can make that conclusion and when you can't. Now, here's I kind of went through this on the last slide, kind of our progression. This notation right here, this f and then the parentheses with the x, is read out loud f of x. So that's how you read it. You do not say fx. Definitely don't say times x. Okay, that's my next thing that's going to pop up on the screen here. It's f of x, which is shorthand for function of x, okay, meaning it depends on x. So that's what that notation is indicating. It's something is dependent on that. It is not multiplication, okay? And that's where it runs a little bit contrary to what you've seen before. You might have been told in a math class before that, hey, if you see parentheses like that, that is multiplication. So 2 parentheses like 3, that's 2 times 3. Therefore, you know, this should be f times x. And I understand why it looks like that. And maybe because this is the exception, this is a new kind of notation. It does not fall under the things that you have been told before, and somebody needs to tell you that explicitly, because yeah, like I would assume the same thing if nobody told me, hey, like, no, not this time, this is like a special kind of notation. It's also one of the reasons we don't use f as a variable very often. We tend to use like x's and y's and z's and n's because we do use the f for that function. We don't want to get that confused. F is the name of the function, and so when you see this notation right here, this is the name of the function. And I ask my students, why do you think it's called f? And eventually somebody says, oh, because function starts with the letter f. Yep. Okay. Other common names for functions are g and h, simply because they come next in the alphabet. So you have A, B, C, D, E, F, G, H. Just they're the next letters. They're the next letters that are there. But you can name your function anything you want. I had a graduate professor that always named his functions Bubba. Okay, that's what he did. He called all of his functions Bubba, probably because the content was really boring and this was about the only thing we could do to make it interesting. So just name all your functions Bubba. But it's the name of the function, and in most of our application problems, there's a reason why we name it that way. The x, or whatever you see in the parentheses, is the input from the domain, meaning this is the number that we take from the first set, okay? So that is what we take from the first set. It's where we start the mapping from one set to the next, is where we start that mapping. So that's what you've got in the parentheses there. And f of x is the output we get from the range, meaning the number it maps to in the second set. So that's why a lot of times you'll see that y is equal to f of x, just indicating the second set. So back when I had that the diagram, and we had the x, instead of calling the second set y, we might call it f of x, just to indicate, hey, this set depends on, or it fits that special kind of relationship as related to this set. And so we've got the input Like, what are we taking from the first set? And then f of x is what we're taking from the second set. So we're just going to take a look at this. So we have here f of x equals 2x minus 4. And the problem there says, what is f of 1? And so the way that we read that out loud is f of 1. In other words, what is the element from the range, okay, from that second set when x is equal to 1? So you've got the two sets, and what this is asking us for is saying, okay, if I pull a 1 from that first set, what is it going to map to in that other set? Okay, so what is that f of 1? What would that be? And the way we just go about doing that is we say, okay, well, we look at what our pattern is. Okay, so it was 2x minus 4. And we're going to pull that 1 from the first set to be our x. 2 times 1 is 2. And 2 minus 4 is negative 2. And so that tells me that when x is 1, the element I'm pulling from the range is a negative 2. So in my little description here, okay, it's like 1 maps to f of 1. I could instead say like 1 maps to negative 2. We have their f of 5. Okay, so 5, like what would this be? So if I pull a 5 from the first set, what would I be getting from the second set? So that would be 2 times 5 minus 4. F of 5 is 2 times 5 is 10. And 10 minus 4 is 6. So if I pull a 5 from the first set, I'm going to be mapping to a 6 in the second set. And I can go up here and erase that and show you, well, there we go. There's our mappings. Now, the screenshot over here, this is from Desmos, and I inputted this in. So if you haven't done this before on Desmos and you've been using Y's are fine, but you can also do f of x's, and you'll notice that it can generate a table, and pretty much you could think of it like this is my first set, and this is my second set, and we are showing all of those mappings, and you could just plug in, like I could go into Desmos and delete those numbers and plug in other numbers to see what they map to. And so here's the one that we were doing right here. Okay, so we did the 1, negative 2. And you can see that mapping right there. Now, what Desmos will also do, though, is it will recognize that notation, and you could pick something else. You could pick anything you want, decimals, fractions, ugly things that you don't want to deal with, and you can plug it in. So we could do f of 100, and it will tell us what f of 100 is. So in other words, if I pull a 100 from this x set in my domain, then it will map to a 196 in my y set, or f of x. So that's what it looks like on Desmos. All right, what's a real life example of a function? Okay. Well, there are lots of examples of functions, but we usually start with linear functions. That's because coming out of Algebra 1, we have studied lots and lots and lots of lines. These are one-to-one functions that will graph as lines when we plot the mapping of x to y. And here's the really good news. Everything you know about lines holds true. So if you know about slopes and y-intercepts and like all kinds of things about lines, like how to graph them and how to solve linear equations, all of that, it all holds true. We just now add this idea of mapping to how we conceptualize them. So we're thinking of lines just in a little bit different way, a little bit of the twist. So the x's are this like mapping over to the y's, and we use that linear equation to generate the mapping. So all the stuff you know about lines, still good. Okay, none of that is gone. We just kind of are adding to our conceptualization of, okay, well, we think of it as in terms of a map. So here's an example. Suppose you have your car in cruise control on the highway, holding steady at 60 miles per hour. The distance you travel can be modeled by d of t. So going back to that notation, that is d of t. And what it means is distance is a function of time, okay? Or distance depends on time. Okay, that's what that means, where D is the distance and T is the time in hours. In other words, if you're in your car and you got it on cruise control, okay, and you're holding steady, 60 miles per hour, you're driving through North Carolina on I-95 and there's like nothing there. Okay, South Carolina, North Carolina, super boring. Okay, not a slight against Carolina, it's just driving through 95 on that road is very boring. Okay, and what we're saying here is that how far you've traveled depends on how long you've been traveling. And so we could see this, we interpret D of T to mean distance depends on time, or distance is a function of time. And so D of 4. Okay, this means we're going to pull 4 for that value of time. And so this would be 60 times 4, or 240 miles. And so what that means is when your time is 4 hours, the distance that you've gone is 240 miles. It would correspond to that ordered pair. And in this case, like in your application problem, you're relating hours to miles using a mathematical relationship. Here's what it looks like graphically. So I actually put this into Desmos. D of T equals 60T. And then I had to tinker around with the window here. But this is the point that we just found. After 4 hours, you would be located right there. And you kind of follow that line back. And this is 200. So we have 210, 220, 230, 240. And so we can see that graphically on the graph, as well as like the algebraic computing it out. And you can see that this is a linear function because when we graph it, it looks like a line. If you wanted to find the slope would actually be that 60 miles per hour. Okay, y equals mx plus b, the m value or slope value would be 60. You can see that right here. Okay, if you look at the rise, goes up 60 over the run, which is 1, so rise over run. And you can see that it's not just like a couple of points, it's an infinite number of points. Okay, infinite number of points that we've got there. So that's just the graphical version of it. All right, so that wraps up this lesson. Please don't forget to like this video if you found it helpful, maybe cleared up some misconceptions about functions. Subscribe for more math content. Please check out the practice set for this lesson and drop a comment or a question below to engage. I'll see you in the next video.